It's great to be here today to talk to you guys about my experience working at Twitter, and specifically around our efforts around decomposing Twitter from a monolithic singles application into a whole bunch of small JVM services. So a little bit about me real quick. I'm the tech lead of a team we call the Tweet Service team. It's one of the core, the tweet service is one of the core services at Twitter. As you might guess, it deals with tweets. The service handles all the reads and writes of every single tweet going through the platform. I've been at Twitter for about 3 years now. When I started the company, it was about 200 people, and it's over 2,000 now, which is pretty tremendous growth. Also, not just has the company grown, but internally, architecturally, things are dramatically different today. Sort of as a backstory, context of what I want to talk about, this graph really speaks and says a lot. It shows that as of sort of early 2013, our users are creating more than 400 million tweets a day. That's 400 million a day. 2010, you could see it's just basically a fraction of that. And before that, you can't even see the numbers on the graph. They're so small. What this really demonstrates is that Twitter has really sort of increased in importance as a communication platform throughout the world. Its importance has gone up, and that means that the cost of failure to us has gone up. Looking at this next graph, which sort of shows site success rate over the years, you can see that it sort of tells an interesting tale. I think the mic was acting up. In the early days, we didn't really have that much site traffic, and it was pretty easy for reliability to be reasonably good. Around 2010, in fact, the week that I started at Twitter, the World Cup soccer matches were happening, and we were in the unenviable position that every time one of the popular teams scored a goal, Twitter would basically fall over. Not a great situation to be in, but site traffic was essentially growing at a rate faster than we could deal with it with the current architecture. So just diving briefly, a little bit of architectural history here. This is roughly what the Twitter architecture looked like in 2006 at the beginning. Storage, basically just a simple MySQL setup, single master, multi-slave. And everything else was handled by this application that we called the monorail. It's our monolithic Ruby on Rails application, sort of lovingly depicted here by Monorail Cat. And this application literally did everything for us. It handled all the routing and authentication concerns, sending requests down to the presentation layer for dealing with handling the HTTP requests, generating the responses, and all the business logic was encapsulated in this one monolithic application. This is essentially the startup implementation you might do when you're getting started. And it worked pretty well for a small number of users. But as you can imagine, it doesn't really scale super well to today's needs. Specifically, some of the challenges that we saw with this early architecture. First and foremost, bottlenecks around the storage layer. Obviously, sort of that naive use of MySQL just isn't going to scale as the number of writes increases. Additionally, Ruby on Rails just inherently has a sort of poor concurrency model, and not the best runtime performance. It's very hard to take a single request and break it up into small tasks that you want to execute in parallel. And those two things combined meant that we really couldn't push any one server to handle that many requests. Really is fairly resource intensive in terms of the number of machines. You can say, well, you just throw more hardware at it. And we did that for a while, but eventually that becomes prohibitively expensive. Additionally, the single monolithic application is somewhat inherently brittle in the sense that if you have a particular feature within the application that starts to fail, it could bring down your entire application. And if that entire application is your entire site, well, your entire site can go down. We actually had like a silly case of a single Japanese translation that actually brought the entire site down. It was kind of silly. On the development side, we were definitely suffering sort of as the company grew beyond the initial few dozen developers up into the 100 or 200 developer range. Definitely started suffering from the too many cooks problem. It's with a single code base, when you have lots of different people all making changes, it's very easy to end up stepping on each other's toes, ending up with merge conflicts, or even worse, ending up with semantic conflicts where things merge cleanly, but the meaning of things have changed. We actually had this really painful 2-week period where we couldn't even get a deploy out the door because we had hundreds of branches that were trying to merge and trying to get a clean build, and just merge conflicts and breakage. We had to redeploy, we rolled back. It was a pretty painful time. Additionally, some of these development challenges, I should say, are partly organizational, and they're not just to blame on the particular technology choices. But we were suffering from lack of clear ownership around various pieces of code, and some of the code had abstractions that were leakier than we'd like, fairly tight coupling between systems, different components. And these things really were roadblocks to developer productivity. It was very hard to make big changes without breaking something. So we set about decomposing Twitter into a set of JVM-based services with an emphasis on reliability. And we set some very specific goals that we wanted to achieve with this change of architecture. One, we wanted to evolve beyond being just a web stack. We didn't want all of our business logic tied up within a web framework. We wanted to be able to use it in new and interesting ways. We wanted to make sure that we focused on isolating responsibilities and concerns around the code so that there's clear ownership of various components. And really what we wanted to do is make sure that the code and the services reflect and mirror the structure of the company organization. So just as there's a tweet service team, there's a tweet service, and there's a tweet service project, and so on. With clear ownership, it's clear who needs to be responsible for reviewing code changes, and ownership means accountability. Obviously, site speed is always a top concern. We largely are addressing the site speed by moving from a slower Ruby-based system to the JVM, where we can get considerably lower latency on requests by doing things in parallel. And obviously, reliability is one of our topmost concerns, largely achieved by being able to isolate failures within particular services and not have them bring the entire site down. And lastly, one of our main goals was trying to increase developer productivity by removing some of those roadblocks that I mentioned. Turns out that this is a little bit of a mixed bag when you go down the service-oriented architecture route. While it may be the case that within a particular team, for instance, the tweet service team, there's fewer roadblocks from other people working on other parts of the system, giving us the ability to move faster. When you need to add features that cut across multiple services, it turns out it's considerably more difficult. And I'm going to talk a little bit more about that in a few slides. And one last point I want to make about a service-oriented architecture that's extremely important is it really helps to enforce that you put in clear API boundaries between various components. As the old saying goes, good fences make good neighbors. An API boundary is really sort of a contract that you're making between different components. And as long as you always obey the rules of that contract, it gives you a little much of a freer hand to make changes on either side. This allows us to be able to replace entire systems as long as we maintain the same API. Oops. So jumping ahead to sort of the 2010, 2011 timeframe, we started down the decomposition road by first attacking some of the problems that we had around the storage layer. Effectively, we wanted to give the monorail better legs to stand on. The first thing we did was we built a storage technology that we call Gizzard, which allows us to take our large data stores and be able to shard them across various storage nodes, and that allowed us to be able to horizontally scale our storage architecture. It's a critical thing for any fast-growing system. We got our tweets all in a Gizzard-based system. We also moved our social graph into into a gizzard-based system called Flock. Flock is actually open source, as is Gizzard, and you can check it out. This really sort of removed some of the I/O bottlenecks that we were having, but it doesn't really address a lot of the sort of organizational and developmental concerns we had. We additionally make pretty heavy usage of memcache for storing things like tweets and users, but we also make use of Redis to cache timelines. A timeline, for those of you that aren't familiar with the nomenclature, is effectively a sequence of tweet IDs. Every user has their own user timeline, which is the sequence of all the tweets that you've created. Every user also has a home timeline, which is the tweets of all the people that you follow, merged together and time sorted. And we try and keep those in cache as much as possible. And we use Redis for that because Redis has a list structure that works out very well for this. So that's sort of the 2010, 2011 timeframe. Today, sort of the 10,000-foot view of what the core platform looks like looks a little bit more like this. At the top of the stack, we have a system we call TFE, which is short for the Twitter front end. It's a reverse proxy. It handles it's the first line of defense on requests coming in. It handles concerns like buffering of requests, normalizing various headers, and so on. It deals with authentication via a separate authentication service. So everything that gets past that routing layer we know has been authenticated appropriately. Next, we sort of hit the presentation or API layer. The monorail still exists today, but it's a much smaller piece of the puzzle. It's currently serving still maybe somewhere in the 30 to 40% of all site traffic, but it's getting smaller and smaller every day. It seems like every week we're bringing up a new service and taking traffic away. And instead of one sort of API or presentation layer service, we have a collection of services that are each sort of narrowly focused on sort of particular concern. For example, there's the main API service, which handles API requests for timelines and users and tweets. There's a separate service for handling the twitter.com web client rendering, which is still sort of a mixture of monorail and this new service. There's a separate service specifically for search requests, and then various features such as whom to follow and activity and discover. Each have their own sort of front-end service. Then all the business logic we've tried to move into sort of this middle tier, which includes the tweet service that I work on, as well as the user service and timeline service, social graph, direct message. Each service sort of organized around what we call nouns, the various nouns of the system, tweets and users. There's a little bit of business logic still in the monorail, but it's mostly out. And the monorail now largely talks to this new layer of JVM-based services. Storage layer looks sort of similar story, but we've added more data stores. Now, one of the interesting things to note about this diagram of boxes is that instead of having one sort of monolithic thing where you're communicating via components with direct method calls, we now have a whole bunch of RPC calls happening. And between the routing and presentation layer, that protocol is HTTP, because it's basically just pushing the request down. Between the presentation and logic layers, it's mostly thrift, or maybe entirely thrift. And from the logic down to the storage, it's various protocols depending upon the storage technology. It's thrift for our Gizzard-based services, or MySQL protocol, or what have you. When we first started down this road of decomposing Twitter, we were in this position where different engineers working on different services were all sort of implementing or copying and pasting their own solutions to problems such as handling failures and retries and load balancing, and doing it somewhat differently for each of the different protocols that particular service had to deal with. There wasn't a lot of consistency, depending on the quality of the engineer. Different services might have different quality of handling these concerns. And so a couple of engineers saw this problem, and out of this chaos fell a system called Finagle, which is open source. It's on GitHub. It's something you can definitely make use of. And Finagle tries to address multiple concerns that apply to multiple different RPC protocols and handle them in a consistent and intelligent way. Finagle is effectively a protocol-agnostic RPC system for the JVM that's very much targeted to high concurrency servers. And it deals with issues such as service discovery and load balancing and sane retry policies, thread and connection pooling, and so on. One of the interesting things about Finagle that I want to just mention briefly is that it promotes a particular concurrency style of dealing with all of your asynchronous code via futures. Futures is something that's probably an entire talk in and of itself, but a couple of key points I want to make about them is that with Finagle, all the I/O is non-blocking, async, and using a small and fixed number of threads, we can handle extremely high levels of concurrency. This makes it relatively resource cheap to be able to scale up the number of requests or connections that a particular server is handling, which was not true at all in the Ruby world. It's a very interesting topic. I wish I could delve into it some more. So I want to dive just briefly, or dive a little bit more into talking about the tweet service that I work on and give you sort of a flavor for, give you the flavor of what the tweet write path specifically looks like. This is something that my team has been working on pretty hard over the past year or two. So just to start with a couple of interesting stats. As I mentioned before, users are creating about 400 million tweets every single day, which goes through the tweet service. That comes out to roughly around 5,000 tweets every single second. We see daily peaks of around 9,000 tweets per second. There's interesting sort of sinusoidal patterns throughout the day. You can sort of see when the East Coast wakes up and when San Francisco wakes up and so on. And we actually hit a max sort of high water mark of over 33,000 tweets in a single second back New Year's Eve in Tokyo time zone, where it's apparently accustomed to send New Year's greetings, and that's sort of translated into the world of Twitter. As big as some of those write path numbers are, the read path, just for comparison, is truly mind-blowing. Daily, the tweet service serves up around 350 billion tweets for all the read operations that we handle, which comes out to about 4 million tweets every single second. Again, there's sinusoidal patterns throughout the day. It's sometimes higher, sometimes less. We managed to serve these tweet requests with about a median latency of about 7 milliseconds and a 99th percentile latency of about 120 milliseconds. The interesting thing to note here is that most requests are bulk requests. So instead of asking for a single tweet, it might be asking, the client might be asking for 200 tweets at one time. And so the P99 latency represents sort of these larger bulk requests. And it also represents a cache miss case because we have a cache hit rate of around like 98%. So those numbers are pretty astounding. You might be wondering, 4 million requests or tweets per second, how many servers does it take to handle that? The server number is sort of in flux, but it's in the low hundreds. So you can figure we're doing sometimes 10, 20, 30,000 tweets per second per box. And we have about 15 terabytes of cache total, which is pretty cool. Now, to talk about the tweet write path, I first have to think about what is a tweet. You probably think of a tweet as 140 characters. And, well, that's true, but it turns out there's a whole lot of extra metadata that we attach to a tweet that adds quite a bit more complexity than you might at first imagine. In this particular example tweet, there's things like user metadata about the author of the tweet. There's metadata about mentioned users. There's metadata about URLs. This tweet is geotagged, so there's geolocation. Has an embedded picture, so there's like metadata about the media. There's also some volatile data, such as tweet counts, like how many tweets and retweets and favorites. And actually, what you see in the in the web client is only part of the story. If you actually look at like the JSON response you get back from the API, there's a ton of other data in there. And we actually have basically almost one service per type of metadata, which is a lot of services for the tweet service to talk to. Now, just diving briefly down into the tweet write path, give you a flavor of what actually happens when you tweet. If you go to your phone, which I did right at the start of the talk, I took a picture of all you guys and tweeted it. That tweet initially hits one of the API layer, the API services at the HTTP layer. That basically takes that data, does some initial validation on it, and then passes it down to the tweet service, which is my service. And the tweet service then takes all that raw data, and it first goes through what we call a compose phase, where it takes the raw data provided in the HTTP request, and it builds up a fully formed, hydrated, as we call it, tweet with all of the appropriate metadata. And that involves quite a few different steps. We talk to a Snowflake server, which is our unique ID generation service. It might talk to the URL service if the tweet contains a URL that needs to be shortened. If there's mentioned users, we talk to the user service to get metadata about them. We get metadata about the user doing the tweeting. If the tweet is geotagged, we talk to the geo service, and so on. There's quite a few different services. And one interesting thing to note is using finagle and features and stuff. We actually do pretty much all of this work in parallel as much as we can. And then we execute in parallel, we bring it back together, and then we've got a fully formed tweet. And then we execute a second phase called the store and deliver phase. As you might guess, we store the tweet in various places, and we deliver it via various mechanisms. Tweet goes to memcache. We do write-through caching. Goes to the persistent tweet store. We index the tweet on various criteria, such as user ID, whether or not it has media, geo, and so on. That goes into a flock-based system called tflock. We send the tweet to the timeline service to deliver the tweet to people's timelines. Hosebird is our streaming service. I have a slide about that in a minute. We send it to the search system to be indexed, and we send it to the mail system to do triggered emails and replication, and so on. And there's a few others that I couldn't fit on the screen. So there's quite a few different things that happen, and again, all of these happen in parallel. Or more specifically, breaking this down, this is just something that's a little cool, and I wanted to share of how we actually break the request up into separate synchronous and asynchronous portions. This is one of the tricks we use to improve the reliability and performance of the system as a whole. As much as possible, we take work that we can do sort of offline that don't influence the result that we send back to the client, and we execute that asynchronously, put it in a queue, and some other server might pick it up. So the tweet service, specifically when we're doing the store and deliver phases, the store phase happens synchronously within the request, so the client all the way back to the phone might be waiting for the response, and we have to make sure that we actually successfully store the tweet before we return a success to the client. But then all these other deliver phases we can actually execute asynchronously because the result of those don't influence the result we send back to the client. So we do this cool trick where we use a system we call deferred RPC. What we do is we take the thrift interface for the tweet service itself, and the tweet service basically makes a RPC call to itself. But what's actually happening is that the implementation of that thrift interface, it actually sends it off to this deferred RPC system, which writes it into a durable queue, and then replays or executes that request against a target cluster. It could be the same cluster, or it could be a different cluster. In the write path case, it's the same cluster, so the request comes back from deferred RPC to the tweet service, and then we can execute the deliver phases. The cool thing that this gives us is that once we've, in the main tweet service, we've completed the store phase and we've returned success to the client, we now need to make sure that we actually execute all these other actions, even if the tweet service that's doing it fails mid-execution, right? So by putting it into deferred RPC in a durable queue, if the tweet service handling the deliver phase fails in the middle, goes down, restarted, whatever, deferred RPC can just retry it. And we make sure that the request and the deliver phase are all idempotent, so if they execute multiple times, it's actually safe. This gives us a high degree of reliability, as well as moving work outside the synchronous path for reducing latencies. It's pretty cool. All right. Next, one of the other actions that I mentioned that the tweet service does is it sends the tweet to the timeline service to do what we call fan out. The idea of fan out is that if I tweet and the 3 people that follow me, they should all see my tweet in their timeline. So the timeline service looks up in the social graph who all my followers are, and then takes that tweet and it pushes that tweet into the cached timeline of all of those people that follow me. And those timelines are cached in Redis. We do like a push operation that if the timeline is in cache, it gets prepended. If the timeline is not in cache, it's a no-op. That way we don't start generating a timeline midstream. As you can imagine, if I tweet and I don't have a lot of followers, this is a relatively cheap operation at write time. When somebody like Lady Gaga tweets, well, she has 30, 40 million followers these days. It's a fairly expensive operation. It's in fact, as you might imagine, a big O of n operation where n's the size of the follower graph. So this is expensive to do on read, but the important thing to note is that we do 2 orders of magnitude more reads than writes. So doing it on read rather than composing the timelines by doing it at write time rather than composing timelines at read really pays off in terms of efficiency. Most active users' timelines are in cache. We have somewhere like 200 million active monthly users. Most of those timelines are in cache in Redis. If you don't visit the site, for a few days, your timeline might fall out of cache. Next time you come, we have to rematerialize it, which is somewhat of an expensive operation, but we don't do it that often. So the streaming service, the tweet service also sends every tweet you create to a system we call Hosebird, which is our streaming API. You might have heard of the fire hose. It's basically the stream of every single tweet that's going into the system. So every 5,000 tweets every single second, we're pumping through the fire hose via stream. I think that comes out to something like 40 megabytes a second of data these days, which is a lot of data. The fire hose is all the tweets, and we have a few partners that have access to the fire hose. But additionally, pretty much anyone can create various other streams that are supported by Hosebird, such as a track and follow stream, where you can go and ask to see all the tweets in real time that match a particular keyword, like hashtag QCon New York. You can basically do, it's basically a cheap way for us to do streaming search. If you use a product like TweetDeck, it actually does this, and it gives you basically real-time updates. You might see a new tweet pop up in your client in 100 milliseconds or less than 100 milliseconds after the user actually send on their phone. It's actually that fast. Additionally, Hosebird supports something we call user streams, which the idea behind a user stream is that it's going to send to a particular user's client all the events that they need to receive in order to keep their timeline up to date. So if you use, say, like Twitter for Mac application, it uses user stream. And what Hosebird does is it looks up, when I make a connection, Hosebird looks up my social graph, caches that in memory, and every time a tweet comes in from one of the people that I follow, it sees that that's a match, and then it sends it through my user stream to my client. And so again, new tweets can pop up in within 100 milliseconds, usually within a second of when it was created. We have like millions of concurrent streams usually active at any one time in Hosebird. Obviously, no one Hosebird can handle all of that, especially with 40 megabyte a second streams. Hosebird actually goes through like 4 layers of cascading to get down to the edge before it gets to all the edge servers, which is, we also have sort of an interesting problem that the size of the fire hose is actually getting large enough that soon a single gigabit connection isn't going to be enough. which is going to be an interesting problem. All right, so that was sort of a quick overview of the tweet write path and sort of where we were back in 2006 and where we are today. I want to distill down for you sort of the top 3 lessons that I've learned working on this. If anything, these are the main takeaways that hopefully you can apply in your own work. So, lesson learned number 1, probably the most important one, incremental change eventually wins. If you want to make a really big change, you can increase your chance of success by making many, many small changes. A couple of times at Twitter, we tried to do something big where we put our head down for 6 months, tried to build something really big, and then bring it up at the end. And invariably, that approach is going to fail. Things on the ground change within that time frame. There's a basic recipe to this approach, sort of rule of thumb. 1, make the smallest possible change you can make. 2, verify that it works. If it doesn't work, tweak it. And then 3, repeat. Just do this over and over and over. And each step, you give yourself a chance to do course correction. And this is the critical part. If you're watching where you're going the whole way and you're making course corrections, you can minimize the risk at each step, and you're more likely to actually reach your destination. This rule of thumb applies to basically all phases of the software development lifecycle. So, for example, it affects or it informs the way that we do deploys at Twitter. General rule, deploy often and deploy incrementally. Back in the monorail days, when the monorail was serving all the traffic, we did multiple deploys every single day, 4 days a week, not on Fridays, because nobody wants to get woke up over the weekend with an incident. But today, the monorail is serving a smaller percentage of traffic. We're only doing about 2 deploys of the monorail a week. But on any one day, dozens of different services might be doing a deploy. And the key thing here is that the more frequently you do a deploy, the smaller the number of changes that you have within each deploy. And that means that it's easier to verify that those changes work. And 2, you've minimized the risk of disruption by changing fewer things at one time. And in addition to doing often, you want to do incrementally. We always deploy a new build for a particular service on a single canary server first, and we watch and make sure that it's healthy. We check stats, and only if everything looks good do we actually then start rolling it out to the rest of the cluster, doing a slow rolling restart of the entire cluster. This rule of thumb applies to how we go about adding a new feature to any particular service. We have a particular system we call the decider, which is a dynamic configuration system that allows us to turn various features of the site on and off. And not just on and off, but more importantly, fractionally on and off, which means that we can turn a feature on for, say, 1% of all traffic, either randomly 1% of traffic, or we can make it sticky like to 1% of users. And so when we develop a new feature, first thing we do is we deploy the build that has that feature with the feature turned off. So the deploy itself is effectively a no-op. And we always have the ability to roll back without actually having affected the behavior of that feature. And then once the deploy is safely out, we turn the feature on to maybe 1%, maybe 0.1% or 0.01%, depending upon the amount of traffic that feature is seeing. And we verify and we increment. So same basic recipe. Do it in a small little chunk, verify, repeat. The same rule applies to things as large as how we develop an entire new service. Rather than trying to do everything in one fell swoop, the basic rule of thumb is, let's say we're decomposing the monorail, we're breaking things off. Try and find like the smallest thing that you can break off to start with. Code that up, create the service, start validating that it works, validate that you've got sufficient capacity for that small thing. Slowly turn traffic up to it via decider. In the case of a service, like if we're developing a new service that is handling an API, we can actually use decider at the TFE layer, which is the the reverse proxy to send like a fractional percentage of requests to a new service. That's sort of a different way of, sort of as opposed to turning up a feature within a particular service. So the moral of the lesson here is if reliability matters to you, and it should, make really big changes in really small steps. Maximize chance of success while minimizing risk. Lesson number 2 that I've learned and that I think we as a company have learned, unfortunately the hard way, is that integration testing in SOA architecture, service-oriented architecture, is actually really, really hard. It's one of the benefits of a monolithic application that if you need to test that something's changed, it's very easy to just launch a single service in a staging environment to test it. When you have dozens of services that all have to work together in order for a particular feature to work, to be tested, it presents a pretty big challenge. I want to dive into just a couple of scenarios of things changing, how we have gone about testing those changes, and you might find some of these interesting and applicable. Scenario 1 is sort of the easy case, where you want to test a change within a particular single service. So this is not a change that spans multiple services. So this really applies almost equally to the monolithic versus SOA case. This is really the easy case. So let's say the change that we want to test is at the API layer. We have a system within TFE, the reverse proxy, called tap compare, where we can send all the normal requests from TFE down to the production API service. But then we can have it send a small sampling of this request in parallel also to a dark system that we're testing, so staging server or whatever. The result of that second system doesn't affect the result that the client sees. It's done in parallel, and the result is thrown away, and it can complete after the original request completed. It doesn't matter. TFE then takes the results from both, writes it to a log, and then we can later do offline analysis of the results. This is great when you, say, are replacing an API endpoint with something that's equivalent, and you want to make sure that it's behaving exactly the same for a large number of real requests rather than just all the things you've mocked up. A variation of this, which applies to things other than to what just TFE talks to, can work at sort of any layer of the stack, is the capture and replace scenario, where you have a production service receiving requests from an upstream client, and it logs some small percentage of those requests to scribe. And then we have a system we call Iago, which is also open sourced. You can write a little code using Iago to have it go and read your scribe logs from HDFS and replay them against a staging server. The cool thing about this is that, one, you have a consistent set of requests that you can replay multiple times, which is great if you want to test how changes behave against a consistent set of inputs. But two, Iago also allows you to replay the requests at a different rate than they originally came in. So this is great for load testing. If you want to test how your system behaves under heavy load, you can replay it 10x the original rate and find your breaking point. And again, it takes results and writes them to a log that you can then analyze later. There's a slightly more sophisticated setup that we use. We use this in the tweet service, where we take sort of live production traffic, and we take a small sample of it, and we send it off to a separate system we call the forwarder. And the forwarder then forwards it on to a staging server to execute the requests. These are mostly read requests, so they're fairly effectless. This is cool because our staging server sees a constant stream of live production traffic. We can easily just deploy a new version of the staging server of the service, and we have live traffic constantly testing. It's great for doing long-running tests and so on. But the cool thing about the forwarder approach is that we can dynamically configure it to fork the requests to multiple targets. So the same request can dynamically be configured to go to a dev instance that you launch based off your feature branch that you're testing, for instance. Additionally, we always have the forwarder sending requests to a system we call the verifier, which then sends the same request simultaneously to production and staging, compares the results. Unlike the previous scenarios where it's writing results to log for later analysis, the verifier actually has an understanding of the schema of tweets and understands what a good result and a bad result is, and gives us live results via a dashboard of verification and comparison errors. So this is great. We can deploy a new version to staging and just open up the dashboard, and we automatically have sort of live results of possible regression problems that have happened with that build. All right. So that was scenario number one, which is really the easy scenario of you're just making a change to a single service. Scenario number two is the hard problem in service-oriented architecture, and that's testing changes that span multiple services. Some of the challenges around this is that if you have, say, 20 different services that are needed to sort of serve the entire tweet read path, how do you launch all of those services with the change that you want to make to all of those services? So for instance, you're making something at the bottom of the stack at the storage layer, and you want to change the result that propagates through the thrift schema of the middle layer that then changes the rendered effect at the API layer. You need to be able to launch all of these services with the changes, and you need to effectively point them all at each other. Like normally in production, we use Zookeeper for service discovery. Well, if you want to launch sort of a one-off instance of Twitter, you need a way to like configure them all to know exactly which service to talk to, and it's a configuration overhead. Additionally, as I said, services may have multiple downstream dependencies, memcache, and whatever. You can't run this all on one box. So just like starting them up on your machine just really isn't an option. And effectively, I'm going to say that this is largely an unsolved problem that we have at Twitter. We can do it. It's just a manual and tedious process. What we'd really like is sort of one button deploy the entire Twitter stack into a virtual environment with everything automatically wired up based off your feature branch that you're working on, so you're not necessarily deploying from master. It would be great. We've had engineers working on it, but there's a lot of hard problems around it. So the moral of the story of this particular lesson is make sure that you plan how you want to do your integration testing strategy early in the process if you're going to go down the SOA route. If you do what we did and sort of think, oh, we have some staging servers, it'll be easy, we'll get it working, you're going to always be behind, you're always going to be running to catch up, and it just gets harder and harder and harder. Oops. Lesson number 3. This is probably obvious to anyone that's worked at scale, but it's something that is important to reiterate. That's that failure is always an option. Particularly when you're dealing with a service-oriented architecture and you think about a single request for, say, a request for a timeline that might look at a couple hundred tweets, that could turn into thousands of RPC calls on the back end to different services and to memcache and to the storage layer. And every single one of those RPC calls, which is a network call, is a chance for failure. So you've basically multiplied the probability of failure significantly. Standard way of dealing with particular network failures is add some retries. Well, turns out retries can be extremely tricky. If you do it naively, the biggest problem you're likely to have is dogpiling requests, and this happens all the time. You have you lose part of your cluster, all the services upstream start repeating requests, sending retries, and now you have the rest of the other machines are now seeing 2x the normal traffic. And they're still failing, and it just gets worse and worse, and eventually everything falls over. You don't want to take this naive approach. You want to make sure that you leverage the knowledge of people that have thought about this. If at all possible, use a library like Finagle, which has thought about some of these concerns and has reasonable retry policies in place. And you want to make sure that you have the ability to route around problems. So if a particular node is down, in your cluster, you want to make sure that your load balancing has a statefulness where it can mark nodes down and stop sending requests to them for a little while. And largely and very critically, you have to make sure that your endpoints are idempotent if at all possible. That way, if you're doing multiple retries and the requests actually succeed, but you can't tell because you never receive the response, you want to make sure that you don't execute multiple effects multiple times in a way that actually ruins your data. So, important rule, you want to make sure you can make your system degrade as gracefully as possible. And what that really means is, one, and this is sort of obvious, but often more difficult than it seems, is avoid single points of failure, right? You want to make sure that if any one node in your system goes down, that's no problem. You have plenty of redundancy in your system. You want to make sure that you over-provision all of your systems. You want to be able to lose an entire rack of servers and still have more than enough capacity to handle daily spikes. Make sure you add redundancy to your data. Have a fallback strategy, which really means that if things start getting bad, what are you going to do? Like if you start losing 25% of your cluster, how can you change your program's behavior in order to deal with that rather than just making the problem worse? One of the approaches which we have at Twitter is have the ability to dark mode a feature, which basically means turn that feature off. So if a particular feature, like say the whom to follow feature, which is not sort of in the critical path, is causing problems, we can just turn it off. And that basically prevents the entire system from failing, right? Now, it's easy to think about sort of the simple failure cases, like a single network server going down, or certain, the network card on a particular machine failing, or a particular rack going down, or a switch, or whatever. Turns out that most of the problems that you might actually encounter are not so simple. They're not full failures of systems. More commonly, you're going to have what are sort of like partial failures, where you have, say, a memcache server that is still accepting requests, but not fulfilling them. It looks healthy at the connection layer, but at the request layer, nothing really is happening. These sorts of cases are actually considerably harder to handle. And importantly, they're actually much harder to imagine. The number of different ways in which things can partially fail is actually mind-boggling. And really the only way that you can gain confidence that your system can handle these various scenarios is really to execute them in production. Actually unplug an entire rack if you're running your own data center, see how your system behaves. Some of the problems around partial failures that we sometimes see is like a particular couple of servers might become very latent because they're very GC bound, because a BIOS setting for IRQ affinity happened to be set wrong, and suddenly all their requests are on the same thread, and blah, blah, blah. And so they become very slow. They're still serving requests, but higher failure rate, timeouts, and these sorts of problems can actually start staggering back up the stack, and you get more and more timeouts. You try retries and dogpiling and so on. I don't necessarily have a good suggestion of how to fix that, but really the moral of the story here is if reliability matters, and it should, you really need to be spending most of your development time thinking about failure cases, implementing failure scenarios, and actually testing them in production. All right, so just to recap, top 3 lessons. These are the key takeaways I think you should get from my experience. Move slow. In order to make big changes, make very small changes. Incremental change eventually wins. 2, integration testing is really hard. Plan your integration testing strategy early, otherwise you're always going to be behind. And 3, remember that failure is always an option. Make sure you spend most of your time dealing with failure scenarios. The happy path is always the easy case. Still have a lot of unsolved problems. If any of you are interested in working on some of them, you can always join the flock. Thank you.